Information in basic analog electronics usually travels as an alternating current. If plotted on a graph, it looks like a smooth, continuous sine wave oscillating above and below zero. But real-world signals pick up amplitude noise, erratic voltage spikes that shoot far outside that predictable path. Feed those extreme voltage peaks into a delicate microprocessor, and the excess energy will completely distort the data, or worse, physically fry the components. To keep these systems safe, we have to establish strict upper and lower voltage limits. We need to create a defined window that the electrical signal is physically incapable of escaping. We need a circuit that acts like a pair of electrical scissors, snipping off those dangerous peaks while leaving the core information untouched. The primary tool for this job is the diode. Think of a diode as a voltage-sensitive one-way valve for electrical current. It stays closed until the voltage pushes in the correct direction with enough force, typically about 0.7 volts for a silicon diode. When that happens, it enters a state called forward bias, forcing the valve open. This schematic outlines a biased parallel Clipper circuit. As long as the input wave stays below the battery and diode's threshold, it passes normally, creating this upward curve. Once it exceeds the voltage limit, V, the diode opens, absorbing all the excess energy. Instead of continuing to crust, the output voltage flatlines precisely at that threshold. The peak is clipped completely off. By choosing a battery with a specific voltage, an engineer can artificially dictate exactly where the ceiling of an electrical signal is drawn. That takes care of the positive peak, but the bottom half of the AC wave is still wild and capable of causing a massive overload. This lower diagram illustrates the double-ended Clipper circuit. We secure the negative vulnerability by adding a second identical branch with the diode and battery flipped. When the wave drops below the negative threshold, -V2, the second diode triggers, shorting out the negative voltage. As the wave flows in, the circuit alternates. The top branch catches the peak, both shut off in the middle, and the bottom branch catches the trough. The sine wave is permanently trapped between two rigid engineered plateaus, and those limits are totally independent from one another. An engineer can set the positive ceiling at 5 volts and the negative floor at -2 volts, customizing the exact shape of the output. Combining these two opposing boundaries creates an impenetrable envelope, ensuring the downstream system receives perfectly processed safe signals. This process serves a dual purpose. Beyond protecting hardware, it acts as a tool for synthesizing entirely new electrical shapes. We've taken a smooth, sloping analog wave and mechanically forced it to mimic a blocky, angular pattern. Modern digital processors do not speak in smooth analog slopes. They require distinct, flat, high, and low voltage states to compute logic. Bridging the gap between the analog and digital worlds requires nothing more than the precise arrangement of 2 diodes and 2 batteries. By manipulating the rigid thresholds of simple semiconductors, engineers sculpt the chaotic energy of the physical world into the precise language of computing.